Started. Looks like everyone found a seat, so that's good. We technically have more people in the class than chairs, but since everything's online, there's no need that you have to show up. So to start with some logistics, I want to introduce our TA, Muzamil, who is standing there in the back. When are your office hours and where are they? And which location?
Can you say that again? We kind of hear you. Oh, I can hear you.
Cool. And if there's a lot of people at office hours, y'all can also come to my office space, which has, I think, more room. And then I also have office hours Mondays and Tuesdays, 11 to 11:30 at post 312B. Any questions on logistics? Okay, well, let's get started. So today we're gonna get into the actual content, and we're gonna start with supervised learning, which was what the big category that's about 80% of this class. And so if we recall from yesterday, supervised learning is all about learning a function. So in machine learning, we have inputs, just like we have inputs to functions in math. So X would be the input, and the output to the model, aka what we predict, yes, y equals f of x. Yeah, I'll write a little slower. Sorry, I got too excited, and the handwriting suffered as a result.
I'm still having this trouble seeing my glasses.
Oh yeah, no worries. Okay, so y equals f of x. And the last part of this is the model, which is the function itself. So in machine learning, the data is the data, and the true value is the true value. That's what you're supposed to predict. But the model is what's learned in the machine learning process, so that given new data, it's going to predict the right thing. So that's all kind of abstract right now. So let's look at our first learning algorithm, which is called linear regression. And as is implied by the name, this is a regression algorithm. So that means it's predicting real numbers. Let's look at an example. So let's say we have a bunch of data, and the x-axis represents, I think this was an example given by someone last class, but the square feet of a house. Who gave this example?
Christoph.
Okay, cool. Thank you, Christoph. And the predicted value of the house is on the y-axis. And we measure a bunch of houses and record how many square feet they have and the corresponding price. And probably in the real world, these would all be in a specific location, because in real estate it's location, but or at least that's what I hear. But for the sake of example, let's say the data was nice and clean and linear like this. What we do in machine learning, given these data, is to learn the line of best fit, and we covered this last class. So specifically, this line of best fit has an equation y equals mx plus b, where, again, the x is the input to the model, y is the predicted value, or the output, and m as well as b are what we call model parameters. parameters. And that's that and that. And so parameters are what the model learns. What the model learns. So in linear regression, this line is the line of best fit. So how do we find out what the line of best fit is? Well, in the case of linear regression, what we can do is measure the distance from each data point to our current model line. And the distance from each point to the line is called the residual error. And we want to minimize the residual error for all data points. We want to find the line that has the lowest residual error. This would be in contrast to, for example, let's draw another line in a different color. We could also have this line, but this line would have really large residual errors. The green lines would have a really high value when you sum them up.
Question?
Yeah.
So with the residual, between the point and the line, is it always a vertical line?
In the case of linear regression, yeah.
In terms of the residual error, that's always linear. Not linear, it's always up vertical, up and down.
Mm-hmm.
Okay.
Yes, exactly.
Okay.
Okay, so I guess let's formalize this a little bit. So the goal of linear regression in a formal manner is to learn the M and B with and there's two terms here, the best fit, you'll hear a lot of people call it that, / minimal error. So error is another term for, in this case, residual error, / minimal sum of residuals. So this is all the same thing, just different ways of saying the same thing. So the line of best fit has the minimal sum of residuals. And we can write that as an equation. So to get there, let's first look at, so last time we mentioned that the true values are represented with y, and y hat represents the predicted values of a model. This is pretty universal in machine learning, it's just notation. So therefore, the residual for one data point, yeah.
How do you type the y hat on the computer? Or how you do that? Y on there,
It depends on the software you're
I mean,
using.
like the text editor, so I'm just trying to copy the notes down.
On a normal text editor, they don't have like Word and other word processing ones should be able to do, but most like just plain TXT files you can't.
Oh.
You could try y_hat if you want. If you're writing in LaTeX, which is it's spelled latex, it's a common text editor for writing equations, you could write y_ and then curly bracket.
Yeah. This is the normal text editor.
Okay. But all these notes will be posted online.
Oh, okay. I don't copy something, just put it online. Got it.
Yep. So the residual for one data point is, and the data point we'll call data point I, would be the absolute value of y sub I minus y hat sub I. So let's slow down, because every time I throw equations at you, I want to make sure we understand that. So let's look at one data point. Let's say we have a data point here. This data point would be y sub I, and the corresponding place on our model would be y hat sub I. So hopefully it's clear that if you subtract y sub I from y hat sub I and take the absolute value, you're getting the distance between those two data points. Any questions so far? Yes?
I missed it. What's the difference between the red and the blue lines?
This line? Sorry. This line?
Yeah.
So this line is just another possible line. Let me give them labels. So this red line is the line of best fit. And this blue / purple line is not the line of best fit. So this is just an example of an other line that could be learned in machine learning, but that would not be the optimal line to make predictions with the data from. Not the optimal model. Any other questions? It's all going to build from here. Okay. Okay, so we have a term, term for a residual, absolute value of y sub I minus y hat sub I, or y hat sub I minus y sub I. It's the same thing because you're taking the absolute value. And notice that it doesn't really matter whether y sub I is up here or down there, because you're taking the absolute value. So even if you get a negative value, the distance is what you'll end up with. Okay, so given that, what we want to do is to minimize. So we want to find the minimal sum of residuals. So the minimal sum of residuals in equation form would be the sum, and if this is new terminology, we will go through it, but sum from I equals 1 to n of the residuals of each data point. Who has seen the summation notation before? Who has not seen the summation notation before? Okay, cool. So I was going to review it, but I guess everyone knows it. But I guess just in case someone didn't raise their hand, this summation means that you're adding up all the data points for where I is a data point. So data point index 1 up to index n, it's like an index in a for loop, of data point I's true value minus data point I's predicted value. And you take the absolute value. So this is what we want to minimize. Okay. So we could write this out even more in a more expanded way as f of, actually, we'll come back to that later. So let's look at the 2D case. So we drew linear regression where we have one input, our x input, and our predicted value y. But now let's just think about what linear regression would look like in 2D. So 2D linear regression. And in this case, we can draw a 3D plot where we have our input 1, our input 2, and our predicted value. And let's say we have data points in 3D, and we kind of drew something like this last class, but just to review, let's say we're trying to predict the house price from both the square feet of the house and the age of the house. Those are the two input variables. Then we might get a distribution like this. And now it's still linear regression, it's just linear in 3D. So that, does anyone know what a line in 3D is? Yeah, okay. So we're basically learning a plane of best fit. Something like that, which would have the equation y equals m1 x1 m2 x2 plus b. So now it's just two inputs, and our weights are now this m1, this m2, and this b. So weights, WEIGHTS, slash stuff the model learns. So that, and that. And you can imagine that this generalizes to more than 3 dimensions, so that in general, in the general form of linear regression, so linear regression general form would be y equals, I keep going to the eraser, m1 x1 plus plus mn xn, and this is really lame at the end, but then plus b. Yes?
Could you lower it a little bit? I haven't quite gotten to the part yet.
Is that good? Okay. So this M and B notation is not super common in machine learning. I like to introduce the concept with that because we all know y equals mx plus b. But when you read machine learning textbooks, the way they tend to write it is either like so, where we say call each parameter subscript what number parameter it is. So this could be parameter 0 plus parameter n minus 1 times xn plus parameter n. It's the same thing, it's just all the learned weights are parameters, because in machine learning oftentimes it's people like to be concise with it and say, okay, we're learning a bunch of parameters, so we're going to call all of those parameter variables theta, so that no matter what we're learning, it's called theta. So it just makes it easier. Another way that it's written is as w1 x1 plus plus wn xn plus b. We'll get to this when we cover neural networks, but W stands for weights, and why it's called weights will make sense when we get to neural networks. But just so you're familiar with terminology, I'm sorry, this is lots of terminology at the beginning, but I want to make sure that when you read machine learning textbooks as supplemental material to this class, you're familiar with the vocab that they use. So and it's often big words for simple concepts, so we just need to get past that and then we can get to the fun stuff. So this B is called the bias, and these weights, or these W's, are called the weights. The parameters, so let's write this as parameter 0 through n are the model parameters. And we'll just emphasize that these three equations are the same thing, just different ways that textbooks write them. Any questions?
So
Yeah.
in the second equation, the bias is the theta n?
Yes,
Okay.
exactly. Okay, so now let's talk a little bit about how the model does the learning. So we know what it's learning parameters for a linear equation, but how does it learn? And we're not going to go into too much details yet, but we're going to start getting there. So the short answer to the question of how do we learn the weights and bias So the short answer, which is all that we'll cover today, and we'll get to the long answer in a future class, is to optimize a loss function. New vocabulary word. So what is a loss function? A loss function, well, I forgot to write answer. Short answer. Trying to make these notes kind of complete so you could just look at them and understand. So loss function is a function which quantifies the error of a model.
Question?
Yes.
So then, gradient descent is one of the ways of minimizing the loss function?
Yes, we'll get to that in a future class.
Okay, I'm just trying to make sure that the loss function wasn't the gradient, it's the way of.
No, the loss function, it's getting us towards gradient descent. I don't want to throw too many things at y'all
Okay.
in one day, so I'm just trying to build up to it.
Just trying to organize my knowledge, sorry.
So the linear regression loss function, every model has a different loss function. So linear regression has its own loss function. And one that we can start with is called mean absolute error, which is often abbreviated as MAE. That's a parentheses. So building off of this term, the summation from I equals 1 to n of those residuals, MAE is basically this equation averaged over all the data points. So the summation from I equals 1 to n of the absolute value of yi minus y hat sub I, which again is the distance from one point's predicted value to its true value, tells us how far apart the model's prediction was from the true value. If we sum that up for every data point, we get the entire model's error. So writing this as an equation, this would be the summation from I equals 1 to n of the absolute value of y sub I minus y hat sub I. Yeah.
What's the difference between little n and big N?
Yeah, good question. I'm being kind of loose with notation here. There's not a big difference. Let's make it all little n. Let's make sure that's consistent. Not, it depends. That's for n and m oftentimes too. But we're not getting, this equation doesn't have any parameters in it. This n represents number of data points. We didn't write this equation yet in a form that includes model parameters. We'll build it up, we'll expand it out to include model parameters as well with a second summation, but we're not there yet. So right now, n only represents the number of data points. In practice, however, we use a slight modification. So in practice, we use mean square error, which is basically the same thing, except now we are looking at the squared distance between the true value and the predicted value. So could anyone tell me why we might prefer MSE over MAE? Sure.
Because when you minus off, sometimes you might, I did an absolute value already. So I was going to say because sometimes when you minus off one from the true value, you get a minus sign. So that's why you square it.
That the square does keep the absolute value property, so that's definitely helps. Yes.
So for a couple things. First, I thought that the mean squared error, there was a square root somewhere also. No. With the reason, I think you do use the square so it's a smoother function, which I think helps with looking at gradient.
What else?
I think MSE is sensitive to outliers, but MSE is not sensitive.
Yeah, these are all good properties. So people like MSE for a variety of reasons. There's also a really simple reason, and that's that it has some nice properties in that it penalizes values that are further away from the true value increasingly more as you get away from it. So if we just look at some examples. So let's say we have the true value is 3, and the predicted values in one model is 4, for another model is 5, and for a third model is 6. The MAE would be 1, 2, and 3 as you get further away from the true value, but the MSE is squared, so it's penalizing, the further away you get, the more it's penalizing the model. And so it has that nice property as well, just from an intuitive standpoint. There's other nice mathematical reasons why we use it, and we'll get to why But just for today, from an intuitive standpoint, this is why we like MSE. So let's start expanding this out, and I think some of y'all have already done this. So let's write now the mathematical optimization objective of linear regression. So math definition of linear regression. And we've built up to this now. So we find, and let's just go back to M and B. The M and the B, which minimizes the average. So basically the MSE, so we're going to write MSE again. But now we're going to, wait, small n, let me rewrite that.
Question?
Yes?
If, if MSE is easier to penalizes the outliers more, then why not use like the cubed error, the error to the fourth power? Why do we stop the squared? Well, actually cubed is possibly.
So if you use cubed, now all of a sudden you'd get negative values if y sub I is larger than y hat, and positive values.
Sorry, I mean, why not the fourth power?
There's, one reason is just simplicity. It's no need to do that. There's other reasons, but we're not there yet.
Okay.
We'll get there.
I'm just trying to, so the other function would penalize it more.
Yeah. So there's a bunch of nice properties of mean squared error. We're just trying to get an intuition as to why we like MSE for today's class, because we're building up little by little. So let's write out mean squared error in a slightly different way. So now we're going to write it out as the true value, y sub I, minus, and now we're just going to replace y hat sub I with w xi plus b squared. And another way to write that is the minimum over m and b. And then we don't need to write this sentence here. So that's a big equation, but we built our way up to it and built the intuition for every little part of this equation. So it looks, if we just started with this, it seems like a lot, but hopefully it's clear that, just to break this up one last time, and then we'll move on, we are finding, this section is finding the average, because if you sum over things and divide by the number of things you're summing over, that's the average. Yes?
Shouldn't the W have a subscript of I?
Good question. So no, and the reason is because the W or the M, I guess it should be M, just to be correct. That's the learned slope of the equation. So let's say you learned y equals 3x plus 1, and then if x sub I is 0, you would predict 1. If you get another data point where x sub I is 1, you still multiply that 1 by the 3, which is the learned slope for the model. So that's constant. The model learns those weights so that whatever data point you give it, it makes the prediction. So the M and the B are learned, and then they're applied to every single data point. That is every single x sub I.
Well, aren't you trying to minimize M and B, which implies that there's more than one option?
There's only one slope, so it's only just a line. It's not like a neural network where you have multiple. You only have one slope.
This is a great question. Yeah, so just to emphasize, when we learn the y equals mx plus b, all of these black data points here are different x sub I. I'm sorry, the corresponding point on the x-axis are different x sub I. So this x-axis are the inputs to the model. The y-axis is what you're predicting. But the line that you're using to predict just has one slope and one y-intercept. That's the same. You have a bunch of different data points that you can predict with using that line, but the slope and y-intercept of the line are constant.
I understand that, I just thought we were looking for n number of dimensions or something like that.
No, so for this equation here, this is just for one-dimensional MSE. And we could write it out, and we'll get to linear algebra. Again, I don't want to throw too much at y'all on one day. We'll start writing this in terms of linear algebra eventually, where it's really easy and concise to write this in multiple dimensions. But if I threw all this at you at one day, I feel like it would be a lot. So just taking it a few steps at a time. But great questions. Any other questions? Who finds this fun? Okay, I'm seeing some nods. Okay, I think this is super cool, so I don't know, maybe I'm biased. Because like now you could make predictions on any type of data, and it's like it seems like such a mysterious black box, but really all you're doing is learning a line, and we all know mx plus b, and so I don't know. I feel like machine learning seems like this mysterious thing, but it's not so mysterious. It's just learn a function that makes predictions for your data. And the machine learning will learn the right function for you automatically. So sometimes, though, you have to give a hypothesis for what type of function it is. So here we're making the hypothesis that there's a linear relationship, no matter how many dimensions there are. We're assuming that it's a linear relationship. But it doesn't always have to be that case. So let's look at nonlinear regression, where we don't assume that it's a linear model. For example, we can have polynomial regression, where now the model that we're learning is ax cubed plus bx squared plus cx plus d. And this is just for one input. So in this case, we have one input, one output, and A, B, C, and D are the learned parameters. So if we hypothesize that the data is going to have a polynomial relationship, then we can train a model to learn a polynomial function. And the model's going to figure out what the A, B, C, and D should be, what the optimal A, B, C, and D are that minimizes the mean squared error. Yeah.
So are the minimum parameter values which you've gotten through just iteration of a bunch of different parameter values and then the computer checks which ones are optimized?
Basically that. We'll talk about the exact algorithm for figuring out the parameter values in a future class. But that's the gradient descent class, which is basically the learning algorithm. But that's a lot. It's kind of complicated. So I think if we understand, basically today is about what are models. Next class is how do you evaluate models. We'll look into coding them. And then we'll look at gradient descent, because I think gradient descent will make more sense once you understand how models work and how you evaluate them. Then it's not too much more to add. How do they learn? And then after that, since we're discussing the broad course, then we'll go into a bunch of different models that learn complex patterns. So that'll be the next part of the class. But these next few are building up all the fundamentals with respect to linear and logistic regression. we're just going to work with linear and logistic regression for the next several classes to learn the entire learning process. Okay, so that's nonlinear. That's polynomial regression. You know, we could also we could have other types of polynomial regression, or sorry, nonlinear regression. So we might also have, for example, f of x equals theta 0 x 1 squared. This is now for a 2-input model, plus theta 1 x1, sorry, x2 squared, plus theta 2 x1 plus theta 3 x2 plus theta 4, just showing you different variations. This would be 2-input quadratic regression, where in this case theta 0 through 4 are the learned parameters, and x1 and x2 are the model inputs, and f of x, aka y, is the model output. Okay. Any questions about this before we move on? Yeah.
Does there have to be that kind of like parallelism between the two inputs, or can you have like higher order polynomials for one input and a lower order for another?
Yeah, you can set it up that way. You could also set it up so that it can have it could have up to, say, 5, up to the 5th power, and the model can learn to set many of the coefficients to 0, the weights to 0, or the thetas to 0, so that in practice it only is a lower order for some variables. But usually you would give it the option to say you can have, you know, theta 0 times x to the 5th plus theta 4 times x to the 4th, dot, 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 for each of the variables, and it might set theta 0 and 1 to 0 so that you ignore the x to the 5th, ignore the x to the 4th for some variables, is usually how that would work.
Okay.
Anything else? Okay. So as we're seeing in machine learning, we could have a bunch of variables potentially, but what if we have too many variables? What can go wrong? So in the ideal situation, when we're learning a model, let's say we have data that are spread out like this. What we want is to learn a curve like this. This would do a pretty good job. But we can get into a situation where two different situations that are on two different extremes of what could happen. So for the same data set, I'm going to draw roughly the same data set. It's not going to be exact, of course, but this roughly quadratic relationship. We can have something called underfitting, where we're trying to apply a linear model to quadratic data. So let's give this the term, underfitting. And sometimes statistics people call this high bias. On the other extreme, you can have a model that learns like this. It hits exactly every data point, exactly. This, by contrast, is called overfitting. In statistics, people like to call this high variance. And this could happen in situations where you have a bunch of model inputs and the model's trying to learn perfectly for all of them. And so in order to do that, it needs a lot of weights, and therefore it's going to learn exactly the pattern of the data without really learning to generalize. And this is really one of the quintessential problems of machine learning, is how do we prevent overfitting, and how do we give the model enough power to not underfit, where we can get a just right model.
With overfitting, you mean it's like memorizing everything instead of finding a pattern.
Yeah, I like that word. So let's add memorizing the data. That's a great term.
What's wrong with over?
So, great question. So let's say, let's add a section on that. So what's wrong with overfitting? Let's zoom in to our overfitted data, and let's do a simpler version where now let's look at a linear relationship. So would you agree that for this data set here, where this is X and this is Y, probably the best model would be a line through this data? So does anyone disagree that the best model, subjective, but probably the best model is a line? Okay. So what would happen in overfitting is we would learn something like this. So even though the best model might look like this dotted line, and let's label the red one an overfitted model. Then let's say you get a new data point over here. So, and we want to make a prediction for this data point. Well, the ideal prediction would probably be where the purple line is. Instead, we predict out here. So it's not predicting to the general trend of the data. It's making really, really, really specific predictions to the random noise in the data. So let's maybe add that term, random noise, in here as well. So the noise, the data. Are people familiar with the term noise? Okay, sorry, question?
So, if we did overfitting for that specific model, like you said, we're running the numbers in the data, but what if this is not noise? How do we know that this is noise and not quantity data?
Yeah, so usually just by collecting more data. So if your data set's this small, then there's not much you can do, and your model's probably going to overfit. So that's, I mean, you could also make a hypothesis about what type of model to use. So if you think, I'm going to use linear regression no matter what, then the model's just going to learn these linear patterns. So even if the model, this is where machine learning insight comes into play, and you need to make hypotheses about the data and say, should I use linear regression here, or should I use a more powerful model that can overfit? how much data do I have? Maybe let me plot the data and see what patterns I see at baseline, things like that. So there's a little bit of engineering that comes into play. But if you chose linear regression, then you would probably learn this purple line for this data. If you chose some higher order polynomial regression, you would overfit. But there's also, sometimes you don't know in advance, and sometimes you want the model to be able to learn complex patterns, but still learn simple patterns if it needs to. And that's our next topic. So one solution to overfitting is called regularization. And if you ever do a data science interview, they love asking about regularization. They also like asking about high bias and high variance. So just like data science interview tips, because I did that less than a year ago. Okay, so one solution to overfitting is regularization. And so let's define it, and then we'll go through an example. There's two types of popular regularization methods, L1 and L2 regularization. So L1 regularization and L2 regularization. Going back to the vocab, so I apologize. So in L1 regularization, what we do is we add this term, which is lambda. It's a Greek symbol. We'll talk about what it means, times the summation of the absolute value of the model weights to the loss function. We'll break this apart in a second. And in L2 regularization, it's very similar. We add lambda times, let me write it down here. Actually, add lambda times the summation. Whoa, I already wrote a summation. From j equals 1 to p of, of the parameter squared, similar to MAE and MSE. The loss function. So let's break this apart. So this lambda, so basically what we're doing here from a conceptual standpoint is we're trying to minimize loss. So let's recall that our goal from up here is to minimize the mean squared error. So let's start with that. So our goal is to find the minimum over all parameters of the mean squared error. So we'll write it in a compact form. Right, so this is from before, minimize the mean squared error. But what we do in regularization is we add, let's look at L2 regularization. We add the sum of the model weights to our loss function. So now this is our loss function. So loss function with L2 regularization is this, where this first term is just the mean squared error. So it's the same as before. We're minimizing the average distance, squared distance, between the true value and the predicted value. That's all that first term is saying. And the second term is saying that we're going to add or penalize having too many model weights. So we're going to, so that's kind of maybe hard to understand. First, let's draw it out. So penalize model weights. So to draw this out, I'm going to draw a type of plot that we're going to draw a lot over the next few classes, where the x-axis represents the potential values of our parameters, or in this case, a single parameter. So these are the parameters for the model. And the y-axis represents the loss or the error of the model. So this would represent, maybe we have this sort of landscape. I think we drew this out last class too, where we're saying we're trying to find this point here with the minimum parameters value. So our goal with regular MSE is to minimize, here, let's even call this MSE. So this is literally a plot of the mean squared error with respect to different values of the parameters, the different learned parameters of the model. If we add the model weights, then we're saying we're actually going to make this value, which we're trying to minimize, higher for the more model weights that you have. So if you have, like, let's do a specific example. Let's go to the polynomial regression example. If you have the a x to the fourth plus b x to the cubed plus cx squared plus dx plus e. If a, b, c, d, and e have high values, you're going to add that to the loss function, and therefore it's not going to be minimal anymore if potentially if you have a lot of values for these. So let's say you learned specifically 3x to the fourth plus 4x cubed plus 2x squared plus 2x plus 3. That means we would add, in this case, we would add 4 plus 3, 7, plus 2, 9, plus 2, 11, plus 3, 14. So add theta times 14 squared to the loss function. Whereas if we had instead learned, let's say 0 x to the fourth plus 0 x cubed plus 1 x squared plus x plus 1, then in that case, we're adding lambda times 3 squared to the loss function. And so in the second case, we're adding less, we're penalizing the loss function less. So penalizing the loss less in this case. Let me explain it in one different way, so maybe visually. So let's say for a particular values of A, B, C, D, and E, we get this mean squared error. But because we're adding 14 squared to the loss function, that brings us this line is going to represent whatever lambda whatever that value is. That would bring us up here. So now our actual loss is up here. But let's say we had learned these values of theta, which at baseline has a higher MSE, but where the lambda times 3 squared is much smaller than 14 squared. And so when we add that to the loss, it only brings us up, oops, let's use blue, it only brings us up here. Therefore, we're favoring the second case because after we penalize having high model weights, then we end up at a lower total loss than we would if we had just looked at the mean squared error without adding extra terms for having too many model weights. So that's a lot. So let's make sure we all are on the same page on this. Yeah.
It looks like we're trying to do linear regression, right? Well, this one has what about negative coefficients that cause the sum to get smaller?
Negative coefficients work the exact same way. So we could, we can make this -2, and we can make this -3.
2 is the theta, right?
Yes.
Oh, I see.
Well, -2 is, sorry. -2 is, but you're either taking the absolute value for mean absolute error or taking the square, which removes the negative, because the negative times the negative is a positive for mean squared error. So either way, the negatives get removed. Yeah.
So the black. So if you scroll down a little bit, right?
Mhm.
No, scroll.
Oh.
Okay, yeah. So the MSE is the black line.
Mhm.
So then if you add the lambda, the penalized model weights, don't you just change the line?
So,
Yeah.
Yeah,
Don't
good.
You just change it to another line, not the black line anymore.
yeah, exactly. Yeah. So maybe let's make this a different color where this purple dot represents. So this black line represents MSE loss, and the purple-ish color represents MSE plus L2 loss. So this point represents the corresponding value of that loss function, which we haven't drawn the whole line for. We've only drawn 2 points, but I could draw an example line. It might not be correct, but maybe that looks kind of like this. I don't know. That curve isn't.
But why would you join between two different poly? Oh, okay.
So we can have different types of loss functions. So depending on the loss function that we define, the model's going to learn different weights. So if we just tell the model to learn with mean squared error loss, it's going to learn according to this black curve. But if we say we're going to penalize having too many model weights, it might learn according to that purplish curve, where even though let's give this name. So this is parameter set A, parameter set B, just so I can explain this. So even though parameter set A has lower loss when you just look at mean squared error, parameter set B has lower loss when you look at MSE plus L2 loss. And we can say that this is parameter set A, and this is parameter set B, so that the picture and the equations are kind of consistent.
But
Yeah.
if you change the line of the MSE, then wouldn't you change the minimum? I thought the whole point was to find the minimum of it. What you said in the last lecture as well, to find that minimum, right?
Right. So this in the MSE plus L2, that point is lower. So you'd prefer parameter set B for MSE plus L2 because for when you're using that loss, parameter set B results in a lower loss value. But if you're using MSE loss instead, then parameter set A results in a lower loss value. And the difference between those parameter sets is the sum of the coefficients or the sum of the weights.
Okay.
So you're basically penalizing your model having too many weights or having too many parameters that it learns. Yeah.
So is that like what is the features, like how many features you're using?
It can, and we'll talk about L1 versus L2 for removing features in a bit. That's a common data science interview question, so we'll harp on that. Yeah.
What is lambda?
Yes. Great question. Yes, we didn't cover that. So lambda equals the regularization strength. It's basically a constant that you define where if lambda is higher, that means that you're going to penalize having weights, too many model weights more. And if lambda is lower, you're not going to penalize it as much. So let's write all that down. Lambda is set by the machine learning engineer. So as a machine learning engineer, you define lambda in advance. And the formal name for this parameter of the model that you define in machine learning lingo, and we'll see this term a lot, is a hyperparameter. The reason for that is that what the model learns are the parameters, so therefore what the user defines are not also parameters, they're hyperparameters, because those are constant sent by the user, whereas what the model is learning are the parameters. So let me make sure I get all this written down. So lambda is set by the ML engineer. It's called a hyperparameter. And just to define hyperparameter more formally, a hyperparameter is a value set by the ML engineer before learning begins. And there's many important hyperparameters that we'll learn about, but lambda's the first. Yeah.
I have a question regarding the regularization. Like in the loss function, doesn't that only penalize the size of the weights? So doesn't it only penalize like if we have larger weights but not the number of weights?
So you're summing up all of the weights, so it's kind of it's penalizing both.
Okay, if I have 0, okay, but like in general, okay.
And we'll look at in a second about how L1 and L2 optimize differently in practice. I mean, you're summing up the weights in both cases, and if you have too many weights or you have too large weights, those are both gonna hurt. But in practice, because of some stuff we'll cover in a bit, L1 tends to set the weights to 0, whereas L2 doesn't do that as much. We'll get to that in a second, though.
So basically what you're doing is you're just adding the weights into the loss function.
Yeah.
You're trying to tell the program, give me a loss function and give me low weights.
You tell the program, here is my loss function, and part of the loss function includes the weights.
So find me a loss function. So it'll start looking for loss functions with lower weights.
You define the loss function in advance, though.
Like, no, I mean, you'll start looking for. So as opposed to a normal loss, regularization will find your function with lower weights.
Yes, yeah, exactly. Yeah.
I think it's not 3 squared or 14 squared. I think that's the square of the sum. I think it should be the sum of the squares. Given
Yes.
the equation you
Yes,
give us.
yes,
So
good
it'll be
point.
like 1 plus 1 plus 1.
Yes. Yeah. good
no, I
point.
just-
No, yeah, that's totally right. So yeah, this was good point. Important math detail is that technically this would be 3 plus 4, 3 squared plus 4 squared plus 2 squared plus 2 squared. And this would be 1 squared plus 1 squared plus 1 squared. So this one's still 3 times lambda. Whoop. And yes, I apologize. I kind of went off the cuff with this example. And this would be, can someone do that math while I answer other questions? And let me know what that sum is. Yeah.
So, can we go back to the formula before the part?
Yep.
I have a question about the P and the summation, the second summation.
Mhm.
So you were saying that we were summing only over the weights. Are we including the pi's in the weights?
Sorry, what was the question?
So we're summing over the theta j, right? Where j runs from 1 to. So what is p here? Are we summing over the number of points, so the weights, the slopes only, or the slopes plus the bias?
Great question. Yeah, so P is the model parameters. And P stands for parameter. Great question.
I have a question about like using the word penalize. So when you're saying penalizing the model weights, like I guess I'm a little confused why we are adding the term and it's kind of getting higher up away from the loss curve. Because when you use the word penalize, I would imagine it coming down or like below the curve.
Yeah, great question. So our goal is to minimize the loss. So if we're adding something to this value that we're trying to make as low as possible, we're penalizing it because we're making it less optimal. The lower the loss, ideally the loss is 0. That means there's no error. If you're adding anything above to that value, it's going to be less good because it's a higher loss, aka more error. So that's why it's penalizing.
So on that thought, like
Mm-hmm.
we're I guess I'm confused, but we go up and we come down. Why can't we just directly get to that second point?
Which point?
So we start with an f of x,
Mm-hmm.
and then you add lambda 42
Mm-hmm.
to you add lambda times 42.
Is that the coefficient? Okay, thanks.
And then you add lambda times 3, and it comes back to the original line.
Mm.
So is there another type of regularization we could have done to do all of this in one step and not two?
No, this is all in one step in L2 regularization. It's just 2 terms of one equation. But in practice, you just input the whole equation and you get to the purple line. I was just showing the black line to show you that without this regularization, you would have gotten to a different set of optimal parameters than if you had not had the regularization. Is that... I'll start. We are getting near class, so I will start next class by continuing on this topic of regularization. Let me just add one more note before we end, just to make this somewhat complete. So just so your notes are complete, let me draw an extra note here. So with MSE loss, parameter set A gives lower loss, but with MSE plus L2 loss, parameter set B gives lower loss. Okay, we'll continue on the topic of regularization on Tuesday. So have a good weekend. Thanks.